say scattering mechanisms. So two kinds of scattering mechanisms I pointed out. One is due to phonons. And what are phonons? Phonons are basically uh, lattice vibrations. Okay, so what is lattice vibration? You have a regular lattice, right? Silicon atoms are sitting. If it is a silicon crystal, then there is a periodic arrangement of all the silicon atoms like this, right? It is not a it is basically a 3D lattice, which is these dots basically shows the atoms sitting at regular positions. Now in our discussion earlier, we assumed that these points are not moving, okay, and we put electrons inside this lattice and we calculated what is called as the energy band structure, assuming that these points which correspond to the position of atoms are not moving. But in practice, these atoms or materials are sitting at a particular temperature, okay. So if you talk about these lattice vibrations, you can say that these atoms or these lattice points, they vibrate in its mean position, and the amplitude of these vibrations is proportional to temperature, okay. These vibrations about its mean position, so therefore the mobility so the mobility that we discussed, whether it be electron, whether it be holes, which are particles or carriers that are going to move through this vibrating lattice. So that mobility is going to depend on, it will depend on temperature. And how it depends, there are various models. So this is mobility by, in the presence of lattice vibration, we say that it is proportional to t raised to minus 3 by 2. So this is just a model, okay. This model is again not very accurate, okay, but this is just a model. How it depends on the temperature exactly, it depends, when you come up with a model, you can say that it is t raised to, so this is also like 1 by t raised to 3 by 2, which means that as the temperature increases, the mobility is going to decrease. As the temperature increases, T increases, we see, as per this model, we see the mobility, which is in the presence of lattice vibration, decreases. Or let me just put it like this. So mobility decreases means the speed of the electrons will be, the drift velocity that we calculated earlier will be less. And why that happens? Because these vibrations will obstruct the motion. Now you have asked how it obstructs, okay. So let's assume that this electron, I cannot really show it like a point particle, it is just a wave, okay. So when the wave comes, all these atoms or the lattice points, they are jiggling in its mean position, okay, in not just in one direction, they are jiggling in all three directions in a very random manner. So the electrons will have reflections, okay. If you consider electrons as waves, then there will be reflections like this, just like we have calculated reflections. So when the electron is going in this direction, some of them goes in that direction, depending upon which way each lattice is vibrating, there will be random reflections in all kinds of directions, okay. If they were not moving, the electron will just move through this without any issue, And that is what we have derived earlier by applying boundary conditions, like periodic boundary conditions. You remember, we took Bloch's theorem, and then we calculated what is called as the energy band structure. But there we ignored this vibrations of lattice in its mean position. Now this t raised to 3 by 2, that is just a model, but this model is not really accurate. Okay, so if you want to know what is the exact dependence, then it will be something like t raised to n. Okay, this n is something that we need to find experimentally if you want an accurate value. But theoretical calculation people try to do with respect to the effect of these vibrations, and they got something like t raised to -3 by 2. But actually it is not. But if I plot it, so let me show some plots. So there are various experimental curves that are available. You can measure these things, and this data is available in the form of graph. Okay, electron and hole mobility in silicon versus temperature. So you have the x-axis, which is a temperature in degrees Celsius, and then on y-axis we have electron mobility. Okay, and these values are going like this: 50, then 100, then it's not really linear. 500, so it is just multiplying by 2. Okay, so this will be something like 200 here. Then you go by multiplying by a factor of 2. That is how the scale is given. Maybe the way I have drawn may not be. Okay, so let me put here. Okay, so this is 500, and then another step you take, it will become 1000, then another step 2000, etc. So if I just draw the case of silicon, which is doped with say 10 raised to 16, then the way it is going to look like, okay, let me also denote, this is 0 degrees Celsius, 50 degrees Celsius, 100 degrees Celsius. This is a linear scale: 150 degrees Celsius, 200 degrees Celsius. Okay, so the curve will actually look like, it will start somewhere here, that is -50. This is -50 degrees. So at -50, the mobility is above 2000. I did not discuss the unit of mobility. The unit of mobility is okay, so we can take this equation like velocity is equal to mu into electric field. So E, I already told you what is the unit, so I don't know the unit of mu. So but this is volt per centimeter, and this is centimeter per second. So we get the unit as unit of centimeter square by volt second. So that's the unit of mobility. All right, so in that we are saying 2000 and 1000, etc. And so when you do experiment, what you do, just like we did the simulation yesterday, we take the reading at different points. Okay, different value of temperature, you keep the sample and you measure these things. You measure what all things you measure, you know the electric field, and you measure current, from which you can measure velocity, and then you take a ratio, and that way you determine your mobility. Okay, so at 200 it comes to be something like 600, 200 degrees Celsius, it comes something like 600, and at 150, it is something like 700 or little less than 700. So it is basically a smooth curve. If you approximate like this, okay, something like this. So the mobility of electron reduces with the increasing temperature. Now, whether it is T raised to minus 3 by 2 or not, that is something that is not clear. Okay, it varies with material also. So, and also it varies with doping concentration. So this what I have drawn here, it is a typical doping concentration, Nd equal to 10 raised to 16 per centimeter cube. Okay, for this particular doping, this is how the mobility varies. Now, if you go to a higher doping, what do you think? Mobility will be more or less? Will this the curve corresponding to Nd equal to say 10 raised to 17, if I look at how will it change? So you will get another curve for the variation with respect to temperature in Celsius, but that curve will look something like this. It is here and here. And this you should be able to explain why this corresponds to an Nd is equal to 10 raised to 17 per. This is another typical doping that we give. 10 raised to 16 is a common doping, which is a moderate doping, and 10 raised to 17 is also sometimes, it's a high end of moderate doping. Anything above 10 raised to 17, like 10 raised to 18, 19, they are heavy doping. Just like I said about Zener diode, they have very heavy doping. So if you go to that level of doping, then what you will see is it further reduces. Okay, so this is donor impurity concentration 10 raised to 18 per centimeter cube. And if I reduce the doping concentration, then it goes upward. So that is quite clear. So there are various mechanisms. When you measure, you can't isolate one mechanism from the other. So this mobility is not just the effect of temperature or lattice vibration, but this dependence with respect to temperature, that is entirely due to or mainly due to the lattice vibration. But the other mechanism that we talked about, which is the scattering by the impurity centers which are ionized, okay, so that is what gave rise to the lowering of this graph downward. So as you increase the impurity concentration, definitely you are creating more such centers of scattering. Scattering centers becomes more as you increase the doping concentration. Okay, but as you decrease, you see the contribution from impurity scattering reduces, because the impurities are very, very far apart for low doping concentration, and as a result you have much lesser contribution from there. But temperature, as you increase the temperature, you have higher and higher lattice vibration, and more probability for collision with the lattice, okay, or scattering. You can, so collision is a word when you assume these electrons as particles, but scattering may be a better word. Why? Because electron is not really a particle, so they have wave nature. So uh, you can do similar kind of experiment in the classical world, like if you send say a wave, maybe a sound wave or something like that, through a medium which has constant density, then it will just move through that medium in the direction of propagation, and it will not be reflected. But Suppose you create some kind of vibrations in that medium, then these waves will begin to reflect from there. So that is an analogous picture you can think about to understand the effect of lattice vibration. Does that help you? Okay. Yes. Yeah. Echo is another way you can think about it, but here you have to. The difference is that these are statistical vibration, which means they are random. They are not in a coherent manner. They are not in a coherent. The vibrations are not coherent. They are random. They are because these are thermally excited vibration. They don't have any specific direction. They vibrate in all x, y, z direction. Okay. uh, so echo means it is an so how does the echo comes that is a good way of looking at it. So echo comes, you have a sound wave which is going like this, and it is going to hit on a wall, and then after hitting the wall, that will reflect back. And the reason is that here medium has one density. Okay, the density here is 1, and here another density rho 2. So there is a sudden change in the density, so that is why there is a reflection. Now if this also have a transmission part which may be less. Okay, the walls also, solids also transmit sound. Any mediums transmit sound, but just like we have calculated earlier with the electrons for various potentials, the transmission probability, reflection probability, this is more like that picture. But what I am talking about in the case of lattice vibration, that is a very statistical. Okay, here and there all atoms are jiggling in its mean position, and they obstruct the wave motion of the electron through it. If they were not moving, there will be no problem. Those reflections we have already taken into account. Those fixed position atoms, they also have some kind of reflection, but that we have already incorporated in the model, and that is what gave rise to energy band structure. Otherwise it would be free electron, right? You remember chronic penny model, we have a periodic potential, right? And every site of atoms have a reflection, and they are cumulative, and they have a phase relationship, and that we have already considered in the model, and we derived the band structure. But what we have not included there is this random motion. So therefore we need to look at it as an additional effect which is not in the model that we have considered. It's a deviation from the ideal model. Yeah. So similarly, we also have characterizing curve. So this thing we can draw for not only for electron but also for holes. And I should also give you some typical values for different materials. These influences of temperature are different. Okay, what I shown is for silicon with the different impurity levels of doping. Now let me give you the value, a table containing value of mobility. Okay, let me change this. So the material could be silicon, the material could be gallium arsenide, the material could be germanium, and the mobility of uh, electrons, mobility of holes. Okay, so we can make a table like this. Okay, and the unit, as I said, it is centimeter square by volt second. This is not velocity, volt second. Here also centimeter square by volt second. And for silicon you should remember this quantity that I am putting it. So for silicon mobility of electron is 1350 centimeter square by volt second, and this is 480. Okay, so this is this table is for since it depends on the doping, so this is like uh, the doping density Nd is something like 10 raised to 16 per centimeter cube at T equal to 300 degree Kelvin. So if any of this parameter varies, mobility varies, these figures are not going to be correct. But this is at room temperature 300 degree Kelvin for a moderate doping concentration. So this is what we mostly use in calculation, these values. So always we take room temperature calculations with moderate doping. Okay, if it is not specified, if it is different, you need to take that accordingly. Okay. Now, but this table also gives a relative comparison with other material. For example, gallium arsenide, it has very high mobility with respect to electrons, whereas for holes it has very low mobility. Another thing, 3900 for germanium and 1900 for holes. Okay, you see around 2.5 times larger. For silicon, the mobility of electrons is 2.5 times larger than that of holes. That means whenever we have an option to make a device using N-type material and P-type material, we prefer N-type material because it will be offering high speed. Okay, so NPN transistor is preferred over PNP transistor. The reason is this: for a given temperature, the mobility offered by, because we are making mostly with silicon, the NPN transistor is the majority carrier is basically electrons, and they offer higher speed compared to the corresponding PNP transistor. Or N channel MOSFET, you will see, is better than P channel MOSFET. So whenever we have an option to use only one kind, we will always go for N-type devices, where electrons are giving rise to the current conduction. Okay, but there are certain cases where we need to take both, so where it is unavoidable. Okay, like CMOS technology, which uses both P MOSFET and N MOSFET, and then we need to take care of the making of the device in such a manner that we can remove that bottleneck. Okay, that means in the design part, the sizing of the device, we need to make the PMOS devices 2.5 times larger in order to get the same performance. Okay, so those are some of the things which will come out of these differences in the mobility for electrons and in the mobility for holes. But and another thing that you see is that gallium arsenide, you see, if you are using N-type material, you get enormous amount of speed up. Okay, for example, silicon, you are able to make a device which will operate at 1 gigahertz. After that, the speed is very less, so you don't prefer it. But gallium arsenide can continue to offer high speed. Even at high speed means you can have higher variations with respect to time. Okay, so for example, high frequency means the electron has to move back and forth at a very high speed. So gallium arsenide is a better material for high frequency application, and you will see silicon we don't use for very high frequency application, especially when you move to like 5G. Silicon is not the material, it is gallium arsenide. And similarly, not only gallium arsenide, there are aluminum gallium nitrate, that is another material. They offer high speed. So devices are chosen depending upon their properties. and mobility is one such property that will play a huge role. Okay, silicon is very good till some frequency, because the speed of electron is limited by the scattering mechanism. Another way to improve is reduce the temperature. Okay, reduce the temperature and keep it in the cooling going on, so that mobility of it will be maximum. But those are having some limitation. Okay, we need to have some kind of refrigeration uh, to keep the device at low temperature, which may not be practically feasible all time. But if you change the material, then you can have high speed devices. Okay, so gallium arsenide, gallium nitride, aluminum gallium nitride, these compound semiconductor has higher mobility, and they are going to be heavily used in 5G applications. Okay, okay, so now if you also want a curve which is relating with the effect of doping. Okay, mobility versus doping. Earlier I draw a curve which connects mobility with the temperature. So similarly you can draw curves, data. I can give you how mobility change with so that is mu e in the same unit, that is centimeter square divided by volt second versus impurity concentration. Impurity. Now if you have a doping from donor impurity atom and acceptor impurity atom, you have to add both of them. Okay, impurity concentration, because scattering happens from both type of impurity. So this is basically Na plus Nd, not just one of them. If both are there, you have to add them. But with respect to the concentration, we have to take the difference. Concentration of electrons will be determined by the difference. Earlier we derived a formula of that kind. But as far as the scattering is considered, they add up. Okay, they don't cancel. All right, so let's look at least our popular silicon. So here it is again. It's a logarithmic scale. So here it is 10 raised to 2, which means 100, and this is 10 raised to 3 multiplying by 10. Okay, in any scale which has multiplication by a factor, that's a logarithmic scale. Okay, so this is multiplying by a factor of 10, just like the logarithm with base 10. Okay, so this will be 10 raised to 4. Now for silicon, now this is all drawn for a particular temperature, that is T is equal to room temperature, 300 degree Kelvin. And if you look at the x-axis, it is starting from 10 raised to 14. This is also logarithmic, 10 raised to 15, 10 raised to 16, 10 raised to 17. So these are the normal doping concentration that we use. Heavy doping means this right hand side, 10 raised to 18, 10 raised to 19. Now if you look at here, though to draw this exactly it is a bit tedious, but let me try. One is for holes. So holes, as I said, 480 is a typical value. So it is somewhere here. This goes up to 10 raised to 16, 17, and then it bends down. Okay, like this. And then for electrons, it's above 1000, and then it also bends down. So this is approximate drawing. What I have drawn here is for silicon. Okay, so this is for silicon material, how the mobility of electron changes. Okay, it's not just, so this is mobility of for electron, mu e, and this is mu h. Okay, so maybe I should correct here. It's not just mu e. Okay, one curve is for electron and the other is for holes. Okay, so this is how, as you dope further and further, what is the impurity scattering, that is the second mechanism. Okay, so I started with the first mechanism. There are two mechanisms. Number one is due to phonons, lattice vibration. The next one is number two. This is impurity scattering. How it depends. Okay, so as the concentration of the impurity, which is sum of Na and Nd. Okay, Na is the acceptor impurity concentration doping, and then Nd is the donor impurity concentration doping. So sum of this, as you vary, so this curve shows this variation. Okay, so now this impurity concentration, it's quite clear. As you have more concentration, you have more chance of the electron meeting these scattering points, right? Because they are very, very close to each other as the concentration increases. So they will be, electron has a charge, so when they come near to this Coulombic potential, either they will be attracted and deflected, or they are repelled and deflected. But in both cases, there is a scattering. Is that clear? Yeah. Okay. So, so impurity the scattering, we can put it as mu I. Earlier I used mu L, so here I can put mu I. So this is the effect of impurity scattering. Now, one question is that how do we combine these two? Okay, if you have mu I and mu L, the resulting impurity. Okay, so combining the effect of 1 and 2. So mu, okay, so this is the formula, 1 by mu is equal to 1 by mu I, that is impurity scattering, by 1 by mu L. Now, how do you get this formula? I will give you a glimpse of what is going on. The probability of scattering, so this formula is derived from the consideration of the probability of scattering, where the probability of scattering. So tau is a mean time between collision. So that means when you reach tau, you will be definitely get a collision, okay, on the average. So if you go a little amount of time, much lesser than tau, then what is going to happen is the probability of collision is going to be dt divided by tau, right? So when you reach tau, definitely there is a collision, but any time before tau, after a dt amount of time, the probability for collision on the average is dt divided by tau. Do you agree to that? Yeah. Okay, so now this probability, the total probability is the sum of the probability due to scattering from one mechanism plus scattering probability of scattering from the other mechanism. So you can write it as dt by tau I That means this could be due to the impurity scattering, or it could be due to tau L, which is lattice scattering. Okay, so this is probability for impurity scattering, that is mechanism 2, and this is probability for um, lattice or phonon scattering. Okay, that is mechanism 1. So from this we are getting this formula. Okay, because mobility expression, you remember, mobility was what was it, q then tau divided by m star. Okay, so this was our expression. So whatever tau is the parameter that through which mobility gets dependent on these scattering mechanisms, where m star is a constant that is basically coming from the band structure that we derived. But the reason for electrons having higher mobility than holes, one of the main reason is the m star. Okay, the effective mass of electron and effective mass of holes. Okay, if you compare, so whichever is lesser will have higher mobility. So effective mass of electrons are normally lesser than the effective mass of holes. Okay, you remember the energy band structure that we had. We had this curvature like this, whereas in the holes we had a curvature like this. Okay, so this is valence band and this is conduction band. If you have higher curvature, that means smaller effective mass. Smaller effective mass, higher mobility. Okay, so those concepts are actually contributing to the difference in mobility for electrons and holes. All right, so now let's go to the next transport mechanism. So I will extend the class a little bit in order to complete this, if it is okay with you. So the next transport mechanism is diffusion current. Okay, electric field giving rise to a current is what we call as the drift current, but there is another mechanism of current flow in semiconductor, which is so the cause for cause is concentration gradient. So we are going to show this. Earlier when I stated about drift current, I said the cause is electric field and we derived the Ohm's law out of it. But now here, apart from the Ohm's law, there is another way current can result. You don't need a potential. Okay, you just need a concentration gradient. Now these are familiar concept to all of you. I will tell you an example. You open a perfume bottle, just open it, take the lid out. Within a short span of time, the entire room will be filled with the smell of the perfume. And what is the reason for this? Diffusion. And what is diffusion? Uh, yeah, I don't know whether scattering is a good word, but you can, they tend to move from higher concentration to lower concentration, right? Now, so same thing electrons also do. If you have one region in the semiconductor where the concentration of electrons is very high, for example an n-type material, the concentration is very high, and adjacent to that, suppose you have another region where, say p-type, where the electron concentration is much lesser. And what is the effect? The electron like to go from n-type material into the p-type material. Now, in the case of perfume molecule, you don't have any electric current. What is the reason? In the case of perfume molecule, when it goes from the bottle to every place in the room, it doesn't result in an electric current. No, 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 no. Listen carefully. I am saying when the perfume molecules go from the bottle into every place inside the room, it doesn't result in an electric current. The reason is these molecules don't have any charge associated with it. But electrons have negative charge, holes have positive charge. Therefore, when they move from high concentration to low concentration, they result in diffusion current, electric current. So that electric current is what we are going to look at. Okay, so let us look at a picture where we have okay, I will consider a concentration variation in say x direction, and suppose this concentration gradient is increasing. It need not be a straight line, it could be like some function like this. So we are focusing upon a particular point, say x0, and then we consider a point which is before it and a point after it. Just like when you study calculus, we define limit like the derivative as a limit. We are doing something very similar to that. Okay, so so we have a point x0 in the x-axis, and what I have plotted here is basically the concentration as a function of distance, concentration of electrons as a function of distance. So now I am going to approximate this curve like this way. Okay, I'm approximating like this. Okay, and as this you can say this is x0 plus delta x, and this one I can say, this point I can say it is x0 minus delta x. Okay, so what is the concentration at x0 minus delta x? It is n of x0 minus delta x. What is the concentration in the next point, that is x0 plus delta x? It is n of, so this is this concentration, and this one is n of x0 plus delta x. Okay, now so this is the concentration at that point. Now if you look at the motion of electron in the x-axis, half of the electron will move to the right, half of the electron will move to the left, because the electron doesn't know where is high concentration, where is low concentration. It doesn't know. They are moving in a statistical manner. So the equal probability for these electrons at location x0 plus delta x to move to the right as well as to the left. Okay, they don't know which direction it should move. Okay, so I am saying it can move to the left and to the right with equal probability. So this probability is half probability to move to the right and half probability to move to the left. Okay, similarly what happens to the electrons at location x0 minus delta x? They also have some probability I mean equal probability to move to the right and to the left. But since the concentration is different, we can see there is going to be a net movement at the plane at x0. Okay, this is larger. They are equal, but with left and right motion, but this is larger than what is moving to the left is larger than what is moving to the right if you consider the plane at x is equal to x0. Is that setting of the problem clear? Okay, okay. So listen carefully. We have plotted a curve which is showing the variation of the concentration of electron with position. This is what we call as the gradient. Okay, the concentration is not constant throughout the material, it is varying from one end to the other end. Rather, from this curve we can say it is increasing. Okay, concentration of electron here is smaller, concentration of electron on the right side is larger. So it is varying from point to point. Now we are looking at 2 points, one on the right side of x0, one on the left side of x0, by a small amount increment delta x. At x0 plus delta x, you have some amount of electron there at that point, which is larger than the amount of electron which is available at x0 minus delta x. Now, what are these electrons doing? They are in a random motion. Okay, so if you consider the motion along x-axis, half of these electron will move to the right and half of the electron move to the left. That's what I have shown with the arrows. Clear? So this same thing goes with the electrons at x0 minus delta x. There also half of the electron move to the right, but half of the electron move to the left. But the total amount of electron available at that point is lesser than the amount of electron at x0 plus delta x. Therefore, if you consider a boundary between these 2 points, that is x0 minus delta x and x0 plus delta x, and consider the motion. So let me look at the motion of electron coming from the right. Okay, I will just make it give more emphasis. This is the motion of electron coming from the right. This length of the arrow determines the number of electron coming from the right to x0, crossing x0, and then another arrow I will put for the electrons coming from left crossing the point. So this is our point x0. Now this arrow has a long length because the concentration here is larger. It is increasing to the right. So half of this concentration is also bigger than the half of the concentration coming from the left side. So there will be a net flow of electron to the left. Okay, this is the difference between these two flux. So there is a flux from right to left, and this is from right to left, and this is flux from left to right. Okay, and this is the net flux, and it is in the left direction. Is that clear? Okay, so now let us make it quantitative. So far I explained everything in a qualitative manner. Okay, so flux from okay, let me use different color. So flux from left to right according to this picture is what? So earlier we have derived the expression for flux same way we can write. It is the concentration at x minus delta x, x minus delta x, uh, into, or half of this concentration will move to the right, and the number that is crossing will be uh, depending upon the velocity constant. So this is n, okay, n of x. I am writing it as a function, n of v. So basically the random velocity associated with we call it the thermal velocity, okay. So Vth is the thermal velocity of the electron, not really drift velocity, it is the thermal velocity of the electron, okay. So flux from left to right is the concentration multiplied by the thermal velocity divided by 2. So earlier we derived something very similar. First I took area of cross section A, okay. Flux is what? Flux is the number per unit area per unit time, okay. So earlier I said concentration multiplied by drift velocity was our flux, okay. But here there is no drift, it is all random motion, okay. And because it is random, I am saying half of the concentration will move to the right. So that is this. Similarly, similarly, flux from right to left is half, but now it is n of x. Okay, it will be convenient if I take it as x by 2 and x by 2, so that this point will be separated by delta x. So here I will put x by 2, x plus delta x by 2 into, again V thermal, okay. So it has the same thermal velocity to the left side to the right side, but this is from right to left. Now this quantity, the bigger arrow, is corresponding to this. Why? Because n of x plus delta x by 2 is larger than n of x minus delta x by 2. So therefore the net flux, therefore the net flux is what? The net flux is, so let me write it as the difference between the second minus the first, that is half of n x plus, we are writing it in the direction of increasing x, okay, into V thermal minus half of n of x minus delta x by 2 into V thermal. So this is equal to, whatever is common, let us take it outside, half, then in bracket I have n of x plus delta x by 2 minus n of x minus delta x by 2, then Vth, thermal velocity. So this is the net flux. Now how is current related to net flux? Okay, now before we find out the current, let us prepare this in the following manner. So let's divide this by delta x, and if I divide, I should also multiply this with delta x. Okay, now then if you take the limit, of this quantity, then what we are going to get is, this is equal to, now taking the limit delta x goes to delta x goes to 0, taking the limit delta x goes to 0. So this is going to be equal to so this is a constant, and what is in the bracket when you take delta x goes to 0, this will become dn by dx. Okay, and then there is VTH into delta x. Now VTH okay, so what I will do is that this delta x, let me do one thing. Instead of making it 0, because if I make it 0, it will this will also go to 0. So what I will do is that I will make it go to L. Now what is L? Where L is equal to mean free path between collision. Okay, where L is mean free path between collisions. Okay, so tau is what? Tau is the time, mean free time between collision, and L is mean free path between. So the relationship between L and tau, L is basically tau into V thermal. Okay, L is the mean free path between collision, that will be equal to mean free time between collision multiply with the thermal velocity. Okay, so now so L is typically very small, so therefore we can say this is a good approximation. Okay, so this is a good approximation for the derivative function. So the constants that I have here, that is VTH L divided by 2 is constant. I will put them together and I will write it as dn by dx. Okay, is that clear so far? Yeah. So these constants I will now give a name. This is called the diffusion, it is called the diffusion coefficient. Okay, diffusion coefficient. So therefore what we said is the net flux, therefore the net flux is equal to diffusion coefficient into dn by dx. Okay, now coming to the current. Okay, so therefore J diffusion for electron is equal to, you have to multiply it with minus q into the net flux dn by dx. Okay, so minus q is the charge of electron, and similarly we can have Jp diffusion is equal to plus q into dp into dp by dx. Okay, because the charge of hole is plus modulus q, charge of electron is minus modulus q. Okay, yeah, modulus, just for clarity, modulus means it is a positive thing. Okay, when I say modulus q, I mean 1.6 into 10 raised to minus 19 coulomb. It is positive. So for electron, minus modulus q, otherwise there could be a confusion whether q is negative or positive. But if I put modulus, it is for sure that it is positive. That's the only reason, just to avoid confusion. Okay, so we got an expression for hole diffusion current and electron diffusion current. So the total current due to electron is J. So this is total current density. Total current density J n. So this is due to electron only. So there is drift plus Jn diffusion. So drift plus diffusion. Now if you remember, what is Jn drift? It is modulus Q n then mu E into electric field plus, now diffusion just now we found out, it is minus Q then dN and dN by dx. This is the total current due to electron, where I have added. So this is the drift current density and this is the diffusion current density. Similarly, for holes, I can put Jp is equal to Jp drift plus Jp diffusion. So that will be equal to Qp mu h E. Here it will be plus Q dp dp by dx. Okay, and the total current is sum of these two. So therefore J is Jn plus Jp, or you can also write it as J drift plus J diffusion. Okay, so you have to add, there are 4 components of current, and if you add and all the 4 components into the total current.